Hey everyone, time to buckle in and do the math. Interference patterns, right? The math that analyzes it all. And keep in mind, the important part of this is to recognize that this math, it was basically, you can think of it very visually as developing it to do with waves, water waves, and then it works perfectly with light. What better evidence is there than a wave nature of light than that, right? So here we go. Double point source slit interference. So it can be double point source or a double slit, right? The pattern analysis, the interference pattern analysis. So again, applies to waves, water waves, and to light. And so we're looking at path differences, as we mentioned in the previous lesson and video, right? So we've got path differences, and if light's landing together there, it can arrive in with constructive interference or destructive. So if they arrive so that this, let me just ungroup this for a sec here, right? So these could have been sent out from different spots and they arrive together, but if they arrive like that, it's constructive, and they have to arrive like this, it's destructive, right? So just all depends on the difference in the path. If the difference was like that, then we'd have destructive. If it's like that, we have constructive, right? So these interference patterns turn out to be useful for measurements with light, as you'll see as we go through this, all right? So kind of like in grade 11, we were able to use standing waves to measure the wavelength of sound waves, right? You can use interference patterns to measure things like the wavelength of the light or the distance between the slits and things like that, right? So first step here, we're going to look at the path difference as we were looking at there. And so we want odd multiples of a half wavelength. Remember that, right? Because of course, if you're off by a half, then you end up with destructive, right? So we're looking at that for destructive interference. And so we have that path difference. We want either a half a wavelength, or we want 3/2 of a wavelength, or 5/2 of a wavelength, right? And so the connection here would be, if you notice, if we have a 2, you have a 3. If you have 1, you have a 1. If you have a 2, you have a 3. If you have a 3, you have a 5. And so, it's pattern recognition at this point, mathematical patterns. And I'm going to show it to you, and it's not necessarily something super easy to recognize right away, but if you take a 2 and you double it, you get 4. And if you take 1 away from that, you get 3. You get 6, you double it. Or, sorry, 3, you double it, you get 6. Take 1 away from that, you get 5. Take a 2, or a 1, sorry, take a 1, double it, you get 2. Take 1 away from that, you get 1, right? So these are all double but 1 less, right? Double but 1 less all the way along. And so is this one, right? Double but 1 less. It's certainly not as easy to see with the 1 and 1. So mathematical representation would be to double it, 1 less, and then we also have this divide by 2, right? So that becomes the 2 can divide into the n, the 2n being just n, and then take away a half. So that's where the n minus a half comes in. Okay, so that's the equation for this. So your path length difference is n minus 1/2 lambda. That's what it needs to be for destructive interference. And so use of this is if you have these numbers, whatever number you don't have out of the bunch, you can solve for, right? So if you had all these measurements from measuring interference patterns of water waves or with light, you can calculate the wavelength, which is pretty cool. For constructive interference, then you just need to have the path differences be whole multiples, right? So you can have 0 difference or 1 wavelength or 2 wavelengths. So this equation, pretty simple to see. Okay, so you have a constructive interference version and a destructive interference version. Fast forward to questions here, we're gonna have to look and be like, oh, that's for constructive. Oh, this one here, oh, that's for destructive, right? So we gotta think of those, pull out those 2 equations and use them accordingly. So second step, this is just different versions of the work, right? Of the further analysis to make it more useful for other things is really what this is about. So if you think of the path difference and you divide it into 2 pieces so that you have equal lengths and an extra bit, right? That's the actual path difference. So there's your isosceles triangle, you got the angles the same, whatever, right? So really that path difference is A, S1, that point A to S1, right? Source 1. So the trick here to make it useful for different things is to think of a point along a nodal line that's very far away in comparison to the slit difference. And that's generally going to be true with light, especially because light, the spacing between the slits needs to be really, really small, and the screen can be, 1.5 meters or 2 meters away. So 2 meters in comparison to 0.0001 meters is obviously fits the description here, right? Of being very far away. So what happens is, as you go farther and farther away, these lines essentially become parallel, like rays of sunshine coming towards you. They're essentially parallel, right? And so that means that parallel lines theorem would mean that these guys would add up to 180 degrees, and so they are 90 degrees, right? So that's just a kind of an approximation tool that works really well. So it's not the last time you'll see an approximation tool like that in math and physics and science in general. Next step then, so we've got the 90 degrees. And so we have A to S2 and perpendicular to PN_S1, right? So PN_S1, basically we have this line segment perpendicular to that line segment, that's all we're saying, and then perpendicular, they're all perpendicular to each other, right? So we have triangle source 1, source 2, and A is, of course, a 90-degree triangle. And, of course, you probably recognize the value of that, right? You got your good old SOHCAHTOA, sine, cosine, tan stuff. And so now we have the advantage of being able to say, okay, sine of the angle that we're looking off towards our point on the nodal line, that's going to be an angle from the center line kind of thing, right? So that's sine of theta. Well, what's sine of theta equal to? Opposite over hypotenuse, right? So path difference over d, right? So path difference over d. So we can, algebraically manipulate this thing and, end up with whatever we want, really, right? So when we do this, we end up with this d sine theta. We recognize from the previous work that that's n minus 1/2 lambda. So that's giving us a new version to work with, right? So now we even have the distance between the slits as part of the equation, whereas before we had that wasn't in there, right? So that makes this little thought process here allowed us to figure out a relationship where you'd have the distance between the slits. And then for constructive interference, of course, you just have the other version where instead of n minus 1/2, you just have m. All right, so we can always make that kind of switch, okay? You need to be able to do that. Now, I wouldn't look at these equations as things that you have to struggle to memorize at this point in your career. Really people are going to have these available to them when they're working with this type of situation, and we'll see that type of thing, like what these can be used for shortly here, right? But so this is an example, right? If you are looking to measure the wavelength of light, that's one of the uses, right? So you could measure over to the first dark fringe, so that would be an n value of 1, right? So we got that value. For destructive interference, you're looking at it, maybe measure the angle, and it's 15 degrees, so you've got the 15 degrees. If you happen to know the slit separation, then you'd be able to calculate the wavelength, right? Just plug in numbers and solve, right? That's outlining an idea of like how you do this. It's just not a number version, but just calculations after that, right? The physics is done. A really neat example of this, the molecular structure of things, crystal lattice spacing. So this is when we are, all right, I'm back. Where was I? Molecular structure, crystal lattice spacing. You can actually use the wave patterns, interference patterns, to figure out the spacing of the crystal structure. So I've always, I remember hearing about nickel crystals. You get like salts, right? Like sodium chloride and so on. So you can actually use light and the interference patterns that it produces to figure out either the spacing or the wavelength or whichever way you're calculating, right? The spacing is really small for this kind of thing. So you actually have to use higher frequency light. So it's actually X-ray crystallography, but it would work for bigger crystals as well, right? So with normal light. So it says, you measure over to the first destructive interference at 15 degrees again. If you have a known wavelength, you can solve for that distance, that the spacing between the crystal structure. So very useful. Next step to make it useful in a different way as well, and this ties the measurements on the screen, the spacing, right? That's going to be super easy to measure, right? So it'd be nice to have an equation that has that. So this one here, okay, we've got a point on a nodal line far away. We've got the distance out from the center line, xn. So if it's the second nodal line, you call it x2 or whatever, and it's just a value measured as like 15 centimeters or whatever. You've got the angle over, and you've got the length, the distance here, L, from the center of the slits all the way to the point. You got your point sources, you got your path difference, a lot of similar stuff here. What we're doing is we're zooming in on this to be able to analyze out the math of this, right? So this blue triangle here, S is your angle, not necessarily the same as theta n, right? So we need to work on that. So this is an angle, and then you got alpha, and you've got 90 degrees, right? So if you look at that blue triangle, you've got this, right? So you've got the theta n prime, this other possible angle here, plus alpha plus 90 equals 180. So you got that, and then with the red triangle, where we have theta n in there, the angle to the nth nodal line, would adding to 90 and alpha also. So you can tell, wait a minute, these are both equal to 90. So yeah, they are the same, right? So basically that's a little mathematical justification that this angle is the same as that one in this scenario. So we can work with sine and cosine tan again, because it's a 90-degree triangle. So sine of theta n prime would be what? It'd be this over this, right? So it'd be the xn number, if we extend this thing out, of course, right? Xn over L, opposite over hypotenuse, right? Opposite over hypotenuse, right there and there. So we have that. And then from before, we know that that would equal the n minus 1/2 lambda over d, right? So we end up with this portion of it as a useful equation to use, okay? So for constructive interference, again, just replace the n minus 1/2 with an m. And yeah, so now you have an equation where you can get the wavelength, or you can get the distance, or and so on, and you have information about distance over to a nodal line, okay, which is nice and easy to measure on a screen, okay? So those are all, we talked about all those things already. It's just what those things are in the equation. And then the other thing would be to have an equation to do with the spacing, right? The distance between the delta x. So the equation we had from the previous page, if we do a little algebraic manipulation, we can solve for xn, and then we can do a delta x, right? x2 minus x1. That's all we're doing there. So common factor out the lambda wavelength there, and the L and the D, and we end up with this, okay? So this part here, we'd have, like if we had the second nodal line, and the first nodal line, we'd have this value here, the 2/3 minus, 3/2 minus 1/2, which is 1. And then think about if we had a different pair of consecutive nodal lines. We had like nodal line 3 and 2. Well, then this becomes 5/2, take away 3/2, which is another 2/2 or 1 as well. So it turns out, if you analyze that for all different ones, yeah, that's just going to be a 1. So that simplifies this equation quite nicely. It just becomes this. We have the spacing, the distance between the fringe spacing, you want to call it, equals the wavelength times the L over the D. The L being the distance from the center to the nodal line, the D being the spacing, and yeah, so obviously that one's pretty handy as well, right? You get the slit spacing. So a bunch of new equations that are just for specific versions of this, or depending on what kind of information you're measuring, right? And so the trick is just to recognize what information you're given, pick the appropriate equation, plug numbers in, okay? The harder part is kind of the analysis of this, and again, the value of this is to recognize that this is all to do with physical waves, like water waves, and then we go and apply it to light, and it works perfectly. So again, super good evidence of wave nature of light. So here's an example here. We've got 2-point sources vibrating in phase. So basically like a two-slit situation, right? And it says the distance from one point of the sources to a point on the second nodal line is 32. Distance from the other point source to that same spot is 45. What's the wavelength? So you're given this information, you're asked for that, you pick the equation that has those things in it, you plug them in, and you solve. I'm going to be saying that a few times in a row here. Okay? And again, you can pause and look. And I'd recommend actually you pause and go back and pick the equation and see if you get it right. Right? So let's do that. I'll encourage that for the next one here. So again, light from a laser shone at a piece of paper with 2 narrow slits cut in it. The slits are close enough together to create an interference pattern projected onto a wall. If the distance from one slit to the second bright fringe, so second bright fringe, and also that it's a bright fringe, right? Notice we're talking about constructive, so instead of n minus the minus 1/2 business, it's just m. And yeah, it's this many meters, so the distance from one slit to that, and while the distance from the other slit is this, so obviously you're going to be able to get a path difference, and wants you to calculate the wavelength. Press pause. Go see if you can pick the equation. Actually, the first step is to even think about what you're given, right? So this is what you're given. This is what you're asked for. Press pause, pick an equation. Hopefully you picked this one, right? So it was the same as the one we just used. Instead of n minus 1/2, it's just the m, right? Plug numbers in, solve for wavelength. Done. Okay. Next, here, a beam of light with a wavelength of 540 nanometers is shone at 2 slits that are separated by a distance of, so you're given a d value, right? 2.8 times 10 to the negative 6, so there's going to be a d in there. And we gave the wavelength as well, and we're asking for a second order maximum, so that's going to be an m equals 2. Okay, that's, again, reading these questions, picking out what you're given is a big part of tackling this. And then the next step is just going and finding the equation with that in it. And we're asked for the angle, right? Calculate the angle formed. So again, go check out, see if you pick which equation, and come back, and hopefully you pick this one, and boom, 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 numbers go in, and solve out for value. Okay, so sine inverse just to solve for theta and plug numbers in. And a beam of light with a wavelength of 640 nanometers is directed at 2 slits if the angle formed between the right bisector and the third dark fringe. Remember, that's your theta, and the theta and prime being the same, 4.2 degrees. Dark fringe, so we have the minus 1/2 version. Calculate the distance between the 2 slits. So we want to know the d value. So this is what you have. You go and pick an equation, and you plug it all in, and you get your answer. Okay, so this would be like getting the value. You can say, oh wow, I just discovered that the spacing between the crystal structure of nickel crystals value. Beam of light directed at 2 slits that have a distance between them, so are given a d value. If the distance between the first and fifth dark fringes is 7.3, so that's an delta x business, right? So first and fifth, and you get your delta x equals going on, right? So yeah, there we go. So we know 4 spaces. Watch for that, by the way. First to fifth, how many spaces is that really? That's only 4, right? Think of 1, and then you jump to 2, 3, 4, 5, and so on, right? But anyways, divide that into 4 equal pieces, and you end up with your delta x. And so then you pick the equation that has that stuff in it. There's your fringe spacing equation with the d and the l and the wavelength, and you calculate the wavelength, right? I forgot to mention that. I suppose that's what you're asked for here. You usually type in like this. I've been typing in like that to emphasize that really we're listing the information we're given and asked for, right? That's what I typically do. And the last one, red light with a wavelength of 600 nanometers passes through 2 slits, strikes a screen located 2.5 meters away. If the distance from the right bisector to the 8th right fringe is 1.8 centimeters, calculate the distance between the slits. Right, so you've got your m for bright constructive stuff. That's the 8th fringe. You get your wavelength, you get your L, you get your x8. That's the one where That's this guy here, right? X8. And the m is 8 as well, and you're looking for the d value. Pick the equation that has that stuff in it, and you plug it in, and you get your answer. So the math isn't super hard. What's a little bit hard is to visualize what they're describing, correctly identify what you're given, correctly identify the equation, and then just the math is pretty simple after that, of course, right? So that's it. The remaining slides here, there's slightly different steps and proofs, but same results. If you're interested and want to sort of go through it again and get used to the idea of looking through developments like that and seeing that you can agree with them and follow the logic there for you to do if you'd like. So very optional. Like, you're probably not going to do it, but this is the math questions to do with it with water waves. Main benefit, of course, I want you to appreciate the fact that these mathematical equations work for water waves and for light. Our focus is, of course, in this course on the light stuff, right? So yeah, there are a bunch. I'm okay if you skip some of those. I'm going to be looking for a good number of them completed well, of course, right? So yeah, there you go. So thank you for watching, and I'll see you next time.